Welcome to lesson 4B. You'll see quickly why this one didn't really go with 4A and why I split them up. This one's about descriptive stats. I'm going to start talking about numbers for the first time a lot because we want to be able to answer questions like this. We've got our hypotheses, we've got our null that we want to disprove. How do we do it? Now, how we actually do it is something we're not going to reach till lesson 5, but in this lesson 4B, I'm going to give you the tools you need to work out the basic descriptive stats. Now, before I go on, and this is in my support notes as well, the moment I start presenting numbers, and there's even the odd equation in there, not that you need to learn equations, you might suffer a bit of shock or anxiety. This is perfectly understandable if you haven't done maths since the early parts of high school. Maybe you did high school a long time ago. There's nothing more conceptually complex than what I've got here, these three questions. Which of these numbers is smaller than 0.05? What is the square root of 16? And can you read a basic graph? What's the most common height? Common frequency, you know? It's not just whether or not you can answer these questions, it's whether or not looking at them makes you fearful or anxious. Sydney University has an excellent, it's called the Learning Hub now, so if I accidentally call it the Learning Centre, it's what it used to be called. There's a Learning Hub for mathematics. The link's here on the screen for you. The link's in the support documentation as well. You can always get in touch with them if anything here is freaking you out. But aside from what's there on the screen, we're talking kind of year 8 maths tops in terms of the level of complexity. The real challenge in statistics, and it happens in lesson 5, is the conceptual leap of the sampling distribution. But that's not calculations, that's more, can you imagine what's going on? So let's get going with descriptive stats. It's just about summarizing data. That's all it is. So whereas inferential stats, which I'll talk about in lesson 5, that's a little more complicated. That's about drawing inferences from the data. So we're just going to be summarizing data in this quick lesson. Here's a field of numbers, just lots of numbers in a random order. What descriptive stats does is just allows us to summarize that. Okay, more simply. This is the same data, but now it's in order, if you didn't even notice the difference. 41 is the lowest number, 93 is the highest number. This next step is the kind of important one. It's suddenly become a frequency distribution. See those little columns with F? That means frequency, which in simple terms is how often the score occurred, how often it occurred. There was 141, in fact I'll go back. There was 141 and there were 2 45s, okay? And there were no 42s or 43s. Or 44, so 1, 0, 0, 0, 2. It's just the number of times a score occurs. That's hopefully easy to understand. But what you also need to understand, because there's going to be a lot of curves coming up, especially in lesson 5, you've got to understand how that frequency tally turns into a graph. So this is from a textbook. I hope this is helpful. You can see that the number 3 occurs 5 times. And if you turn that frequency distribution into a graph, then you see that, yeah, the number 3 is 5 yellow squares high. Get rid of the yellow squares, you're left with a line. That's a frequency distribution. If you can get your head around that, then the many curves I'm going to show will help. Here's an example. Here's a frequency distribution of Psych 1001 enrollments. You can see lots of people are studying Psych 1001 from the Bachelor of Arts, quite a few from the Bachelor of Science. Bachelor of Psychology is very large, but it goes all the way down. I've probably had to cut this off because it goes all the way down. Bachelor of Design Computing, welcome to the course. Not so many people, but that's a frequency distribution. Each category and how many people in each category. Simple as that. This is, I've got another example. This is the language people speak, their first language. And you can see English is the most frequent, but in fact, this goes all the way down too. I've just cut it off at German. A few people speak German, Japanese, and so on. Hajime mashite. So frequency distributions. I will return occasionally to frequency distributions to kind of refresh that understanding. But I'm just going to race through some measures of central tendency. The mode, the median, and the mean. What's the mode? Simple. The mode is the most frequent score. With that set of scores there, 1, 4, 2 5s, 2 6s, 3 7s. It's easy when you got the frequency distribution. The mode is 7. It's, for example, here we can see people's origin. The mode here, and again, I've had to cut it off. People come from many more different places than Taiwan. But you can see the mode is Australia for place of origin. That's the mode. And the fact that I have cut this off after Taiwan tells you almost immediately that one problem with the mode is that you don't need to look at all the scores. You don't need to take into account all the scores. You literally can't. You are literally just hacking off the top part of the distribution. The mode here, TV viewing per day, the mode is 3. It's the most common score because 3 occurs 5 times. So look, it only gets complicated when you've got more than one mode. It's just called bimodal. I suppose it's not that complicated. In this set of scores, the number 4 occurs twice and the number 8 occurs twice. So there are 2 modes. There could be 3. And so on. This is an example of a bimodal distribution, which makes perfect sense. This is how many customers in a restaurant. And it's bimodal because you get a peak of 18 customers at midday, the lunchtime rush, and 7 p.m., the dinner time rush. Maybe there are 18 chairs in the restaurant. That might explain it too. That's a bimodal distribution. But you can see the mode is just taking the most frequent score. It's really easy to calculate. And look, the advantages are that it's unaffected by extreme values. It is very useful for qualitative data when you're recording people's responses. And data which is not continuous, so place of origin and so on. But the disadvantage is that it's clearly not based on all the values. For example, with the restaurant data, you're just ignoring everything except those 2 peaks. So as a measure of central tendency, the fact that it's based on very few scores is not great as kind of the mode being representative in that sense. Let's move on. The median, the middle score, you put your scores in order and you pull out the middle score. And when there's an odd number of scores, as there is on the right, that's very easy. 6 is the median. Gets a little fiddly on the left. I will never ask you a question like this in the final exam, but just know that if you've got an even number of scores to get the median, you actually take the average of the 2 scores in the middle. But don't stress about that. There's even an equation there. Don't worry about that. I just needed to do it for completeness. Look, the advantage of using a median, the middle score, it is taking into account the other scores, unlike the mode. And it's going to be unaffected by extreme values. And that's a powerful advantage. That's why, 20 years ago, you wouldn't have heard of the word median outside of a stats lecture. But if you grew up in Sydney or Brisbane, oh God, I suppose it's everywhere now, everything's so expensive. You always hear median house price, median house price. Why not average house price? Because those are averages, means, as we'll reach in a moment, are affected by extreme values. Medians aren't. You put them in order. The fact that the most expensive Vaucluse mansion costs 80 million, whatever we're up to now, that's kind of irrelevant. You just put the prices in order, pull out the middle one, and that's quite helpful when it comes to understanding house prices. It's still not based on all the values, though, in terms of it's putting the values in order. That's helpful, but it's not based on the value of all the values, as it were. Heading towards the mean. The mean is what we use in stats. The mean just means average. And if that just scared the crap out of you, that equation, just look at the description on the right because it means exactly the same thing. And it's all you need to know To get a mean, you add up all the numbers, you divide by the number of numbers. That's what it means. The good thing about the mean, its strongest advantage, and the reason why it's kind of all I'm going to use from this point on in terms of statistics, is it takes into account all scores. But as I've mentioned already, because these were the advantages of the other ones, it is affected by extreme values. I'll give an example in a moment. It's also, the mean doesn't necessarily represent something meaningful. Remember I mentioned for the mode, it's kind of useful for qualitative research. When it comes to turning things into numbers and taking the average of numbers, the mean, you can sometimes end up with some odd statistics. The average Australian family might have 2.5 children. What the hell is half a kid? There used to be a Toyota commercial, you know. The average Australian family has 2.5 children, and there was this little kid. I'm the half. Very cute, but kind of meaningless. What's half a kid mean? Yeah, so the mean, yeah, it doesn't always give you something meaningful, paradoxically enough, but it's mainly, the main issue with it is it's affected by extreme values. So I'm just trying to represent it visually here. Planets, house prices, circles, whatever, the average size of the red circles is the green circle, but the mean you end up with isn't very representative of any of the circles. It's somewhere in between the absolute biggest and there's a long way till the next one. If you were to take the median though, then you're going to get something that's a lot more representative. And I think I may have created a perceptual illusion here. I swear that green dot is the same as the middle red dot. Just looks smaller, doesn't it? Do something with numbers. This might make a bit more sense. Imagine you're doing an experiment and you're timing how long it takes someone to complete a test, and you've got 7 participants. Someone takes a minute, someone takes 5 minutes, everything in between. For the data on the top there, the mean, the median, and the mode is 3. 3 minutes, all the same. The data on the bottom is identical, but like the really expensive Vaucluse mansion, someone has fallen asleep and it takes them 54 minutes. The median and the mode are still 3, unaffected by extreme values. The mean is now 10, and 10's not representative of anyone. Now, of course, in a real study, you can clip the outliers, but even if you are clipping outliers, there's all kinds of means formed by erroneous results, which are going to affect your scores. So that's our measures of central tendency, the mode, the median, and the mean. There are also measures of variability, the shape of the distribution, the range, and the standard deviation. So let me talk about those now. Again, looking at shapes of distribution, we've got to turn a bunch of numbers into something we can see. So let me take a tally. Okay, I promised I'd go through frequency distribution several times. So here it is again. How many times each score occurs. And you can see the shape there in the tally. And the shape, the curves you see in statistics, that's just kind of the frequency distribution drawn as a line. So I'll go back to this one again. Same thing, right? So hopefully we're yet again on the same page. So we can look at shapes of distributions now. We've got possible scores and the number of people who got each score. And there's usually a bump in the middle because the score in the middle is often the most likely. Not all distributions, but that's why there's often a bump in the middle. This kind of distribution is symmetrical. It's very neat. There's, a mode, the median, and the mean are all in the same place in the middle, and you have an equal number of scores above and below. But you can also have what are called skewed distributions. This distribution is positively skewed. Most of the responses are to the left, the lower scores, but there's a handful of really high skews, giving it that positive point. This distribution is negatively skewed. It's the opposite, where most of the scores are quite high, but there's a point heading off to the left. That's how I suggest you remember what positive and negative skew is. The skew of the pointy bit in a negatively skewed distribution is pointing in the negative direction. See if I can give you some examples of this. This is real data from Psych 1001. This is the stage of degree people are at. And you can see it's 1,000 people on the y-axis, you can see that most people are starting in first year, which makes a lot of sense. You do your first year units in first year. Few people doing Psych 1001 from the second year of their degree. Few in the third year, fourth and fifth year. Yeah, because they've got a few electives to make up at the end of their degree, and they heard just how good Psych 1001 is, because it's awesome. It's a lot of work, but it's an awesome unit. That's positively skewed, isn't it? Because most of the people are in first year, the first year of their degree or the second year, but there's this long skew. The other comment is you often get positive skews when you can't go negative. First year is first year. There's no one in high school in Psych 1001. So the fact that it's all bumping up against first year means it's no wonder you get a positive skew. You can't have a long tail to the left of first year. It's just not possible. Number of sex partners estimated across the lifetime. The thing about graphs like this, men lie. Look at all the men who think they've had more than 50, unless there's an awesomely huge amount of gay sex going on in the world. That's plausible, but I suspect that the reason for data is men just lie their asses off. But this is a positive skew. For the same reason I just mentioned, that you can have no sex partners, or one or two, and you can see most people are, 0, 1, 2, 3. By 5, it's kind of crashing off there. But there's nothing below 0. If you have a bad sexual experience, and I hope you guys have done your consent module that the university's asked you to do, but if you have a bad sexual experience, you don't get to subtract your partners. So because all the data is being pushed against 0, and you don't ever get less than 0, that's why you have this positive skew. What was my negative skew? Okay, negative skew example, age of death, okay? Look, there's nothing more tragic on this planet than children's hospitals. Oh God, I just thought of something. Yeah, children's hospitals being bombed by despots. That's tragic. But for the most part, we hope and pray that our children are safe and live a reasonably long life. And yet we know that death is coming. In our 60s, in our 70s, that's the age of death. Why? I don't know where this data is from. I don't know why so many people are dying in their 60s. Yeah. Anyway, it's just an example of negatively skewed data, because you can't die before the age of 0, so there's the limit there, but also there's the limit, all the data is pushing up against old age. That's when people go, and that I just don't think the peak is at 60, but wherever the peak is, it's going to be pushed against the positive side, thank God, which makes this negatively skewed. So think of skew, think of point when you're describing distributions. I've mentioned this already in a symmetrical unimodal distribution. The mode, the median, and the mean are all in exactly the same place. But when you get skew, going back to the first part of the lesson about how the mean is affected by extreme values more than anything else, the mean is dragged the furthest in the direction of the skew. Median less so, mode, not at all. And it's the same if you flip it over. The mean is dragged the furthest, followed by the median, followed by the mode, which doesn't care. Remember, the mode is always the peak of the distribution because it's the most frequent score. Another way to describe the shape of distributions is their variance. And there's several ways to do that. The simplest way to talk about how much scores vary is the range. The range is the highest score minus the lowest score. That's it. There's nothing else to say about the range. It's not very exciting. The interesting question here is, if you look at the red distribution and the black distribution, yeah, there's probably a difference in terms of range, but there's also a difference in the way the scores are spread out. So how do we measure the spread of scores? How do we describe the spread of scores? We use something called deviation scores. And I'm going to use a very small data set with just 4 numbers here, 5, 5, 6, and 8. First thing we need to do is get the mean of those scores. So we add them all up and divide by the number of scores. 24 divided by 4 is 6. The mean is 6, okay? And what we do with that mean of 6 to make deviation scores is we take it away from each of those scores. 5 minus 6, negative 1. 5 minus 6, negative 1. 6 minus 6, 0. So, and let me just pause there. Deviation scores are deviations from the mean. So if the mean is 6 and your score is 6, the deviation score is 0. For 5, it's 1 below the mean, negative 1. For 8, it's 2 above the mean, 2. Okay, so deviation scores. Maybe we can use deviation scores to work out the average deviation around the mean, and we have this really good measure of variability. Problem is we can't do that, because if you think about what we've done, we've taken, have I got a picture coming up of this? Yeah, I've got a picture. What we do when we calculate the mean is essentially the balance point of the distribution. So some scores above, some scores below, perfectly balanced. And this is why deviation scores always sum to 0, because they're deviation scores around the mean. The mean is in the middle of the middle of the balance point. Of course they add to 0. And you know what? When you're working out things and you're working out deviation scores, you can check that you've done the right thing by adding them up, because they should add up to 0. So we can't get average deviation scores if they all add up to 0. You can't divide 0 by anything or your calculator goes nuts. So we need a different way to do this. And we get what's called a standard deviation. To get a standard deviation, we're on our way there. We've done the right thing. We've got our deviation scores. We can't do anything with the deviation scores though, because they add up to 0, but we can square them. We square the deviation scores, and suddenly negative 1 becomes 1, negative 1 becomes 1, because a negative number multiplied by itself becomes a positive number. And then when we add those up, we don't get 0, we get 6. We get something we can do something with. Now, what we do next is we then, again, look back. We've got 4 scores. Little n is the number of scores. We divide the number we got. Now, this is not the mean I'm working with here. This is the sum of the deviation scores. 1 plus 1 plus 4 plus 0 plus 4. You might think of the sum of the deviation scores squared as the sum of squares. You might read that a lot when you're reading about stats. We simply divide that by the number of scores to get what's called the variance. Okay, so it's not that exciting here. The variance is 1.5 for this tiny set of numbers. Now, obviously, the bigger that number, the bigger the variance, the more scores vary, but it's not quite what we want just yet. We want to take the square root of that to get our standard deviation. Okay, which is like an average deviation, but you can see the hoops we had to jump through. We had to square everything. Now we're bringing it back again. We're taking the square root. So our standard deviation for these scores is 1.224. Understand where it's come from. Okay, we find the mean. We find deviation scores around every score. We square them. We add them up. We divide by the number of scores. We take the square root. Okay, understand this procedure. There's even a sheet in my support notes where you can have a practice. Sorry, didn't want to scare you. Yes, there is an equation. That's the equation. But you know what? If you can read those 6 steps and do those 6 steps, as I just took you through with a table, yeah, you don't need that in first year. So don't have nightmares about that. So understand what a standard deviation is, understand where it's come from. That's an important learning outcome. And you know what? Knowing how to calculate a standard deviation by hand is really going to help you understand, because as you do that, you'll get a sense for where it's coming from. When you look at an abstract set of data like this and you see the standard deviation is 16, you can have a better grasp of what it means. This is research report data from 2021. This is scores for the research report. The mean was 57.9. The standard deviation was 16.4. So on average, scores are varying around 16 around the mean. You can actually see that on the graph where there's a lot of marks in the 40s, low 50s, and heading up to 60s and 70s. And that's kind of capturing where most of the scores are varying on average. The other thing you'll notice if you do this by hand is what impact the variability of scores will have on the deviation scores, and then the deviation score squared. So look at those raw scores now, 5, 5, 6, 8. They're all very close to 6. They're very close to the mean. What if the scores were 2, 8, 10, 4? Same mean, 6. But now the scores vary greatly around the mean. The deviation scores have rocketed up. The deviation scores squared have rocketed up even further. I'll switch back and forth a few times. You know, the sum of the squares of deviation scores was only 6 in this low variance sample, if you like. But now it's rocketed up to 40. That gives a very high variance and a standard deviation of 3, whereas before the standard deviation was only 1.2. So if you do it, there's some sheets you can do it by hand in the support documentation, and even in the support module, which is kind of a bit of out of date now, you'll get to see me do it by hand if you really need to see someone work out a standard deviation. But if you're wondering, oh, do we have to do it by hand in the exam? No, but you have to understand. You have to understand it backwards and forwards and upside down, like all these other concepts. So doing it by hand will help you understand what's going on. So that questions like this, which seem so abstract and wacky, it's easy. Which distribution of scores has the largest standard deviation? The red one. They're more spread out. Simple as that.